Um, we have our next speaker now going to take the stage. The name of the talk of the next session is Navigating the Perfect Storm, Enabling the AI Era. I want to call to the stage Shaul Cohen. He is the Algorithm Group Manager of Applied Material. Please, the stage is yours.
עם מה אני מעביר? Hi all, I'm Shaul Cohen from Applied Materials. Sorry for my voice, I'm a bit sick. So I would like to talk about a different perspective on the AI technology that we are all here for. So during the last 2 decades, we are experiencing, all of us, a change in how we use computers. The first wave started with the PC and the internet era, which increased demand for computers. And after that came the second wave of mobile and social era, which all of us has at least one cell phone in our pocket. And the next wave, which already started, it's the AI era with big data. And there are many phrases about that. One phrase that catches me is from The Economist, that the data for us is what oil was for the last century. And now let's go under the hood and think what we need for AI. So AI, for using AI, we need it stands on 3 legs. First, it's data generation. We need huge amount of data to feed into our algorithms and to create these sophisticated systems that can recommend us, for example, when you buy this bag, I recommend you also to buy this pen. So we need huge amount of data. And we are experiencing today explosion of data. In a minute, we'll see more. The next leg is data storage. We need a place to put all this huge amount of data. So there is an increased demand for memory, for storage. And the last stone is computing power. We need computing power in order to harvest all this data and to use it and to take it from the data to extract knowledge. So these are the 3 stones that we must have in order to proceed with and build very sophisticated AI algorithms. So let's talk about a bit the data. In 2018, it was an inflection year that the data that humans created was less than the data that automatic machine created. And we see that it's exponential, that will generate more computers, an automated system will create more and more data. And for that, we need storage. And we know that we need to improve computing power very dramatically in order to harvest all this data. And everything is great, and now comes the but. But what we see is that the computing power is getting slower. The improvement in computing power is getting slower with time. On the right graph, we can see that during the years, the percentage of improvement is getting slower and slower. And on the right graph, we can see that passing from node to node it means shrinking the devices, takes more and more time. We can see that passing from 40 nanometers to 10 nanometers took more than 4 years. So that's a problem. And there are many companies that looking on hardware today, and hardware wasn't sexy till the last year, and it's getting a bit more sexier to tackle this problem, to create new ways, new architectures that we can, new computing systems that can that can bypass this slow of improvement. But there is one thing in common for all these developments. It's to create structures, meaning devices, transistors that are denser and higher. So that's the problem of the designers. It's not related to us. We can think about that. But now let's see how making devices smaller and higher relates to computer vision algorithms, to AI. So in Applied Materials in Israel, we think about it that we are the eyes of the fab, meaning we are taking devices, taking images of devices in very high resolution. You can see the numbers here in nanometers. And we need to do measurement and characterize the device and say whether the device is working correctly or not, and help the manufacturers improve the computing powers and make the devices smaller and higher. Okay, so just if you want to understand the numbers, we are talking about nanometers. So typically our resolution is 1 nanometer. That's the resolution that we are looking at. Blood cell is much bigger, 7,000 times bigger. Just another 2 examples. Bacteria, that's the size of bacteria, and virus, which I have one now. So we talked about dense and higher structures. Okay, so let's go even deeper and talk about these 2 elements. So let's start with higher structures. So when we're looking on wafer, it's where we are producing all the chips. Looking on wafers, it's like looking on Earth from outer space. So let's zoom in. And more, we're getting more and more closer till we'll get to the resolution that we see it in our images. We are targeting Manhattan. Okay, till now we are in the same resolution. But in our systems, the magnification is much, much bigger. So what is 3D characterization? 3D characterization, it means let's think about the building that we see in the image. Okay, the devices that are produced are more like we can think about them as buildings. We need to characterize the 3D structure, meaning to measure the height of the building, to measure, to count how many floors we have, to identify which floor is higher than the other floor. And all these parameters are really, really important in order to make the device work, to make the i7 or whatever work. And when I showed you this image, I'm a bit cheating because this is easy. Okay, looking on one building, that's easy. The real problem in the semiconductor industry, it's more like that. The distance between buildings, it's 1 meter. And that's a problem that we need to tackle. And the 3D reconstruction, it's a crucial part that we need to find a way to solve. And currently, I can tell you that there are a few solutions, but there is no holistic solution for 3D reconstruction in the semiconductor industry. And that is a barrier for hardware development. So we talked about building higher structures. Now let's talk about dense. This is illustration of an image. Because of IP, I cannot show you real images. But just to, so you can have a glimpse of what dense mean. So let's zoom in a bit. Dense mean that in a space of a few pixels, 1, 2 pixels, one segment from the other, that's the distance from one segment to the other. So the challenge is is to segment correctly each feature and then to do the measurement. And we need to be really, really accurate in terms of mistakes of 1 pixel, 2 pixels that can change completely our diagnosis. For example, there are 2 mistakes that we can make. One mistake is segment wrong and then declare that this device doesn't work, even though it does work. And that will create a problem for the factory, which is okay. It will cost money, but okay, not our money. The other problem is when we'll say that the device is working, where in fact it doesn't. So you can imagine that you are driving in your autonomous car. I don't know if you can call it driving, if the car drives itself, but that's for a different topic. So you're driving in your autonomous car and everything is great and you're going to the highway and the speed is 100 kilometers per hour. And then there's a blue screen. Fatal error, blue screen, what would you do? So this is extreme scenario, okay? But accuracy and identifying whether the device is working or not is really, really important. So just to get a glimpse of numbers, for this talk I collected the numbers of mean IOU for semantic segmentation on several benchmarks. I took many benchmarks, and these are the points during the years, the last years. And we can see that the state-of-the-art work is mean IOU of 89% work of Google. And I'm sure it's great for the, I'm imagining let's go again for the example of autonomous cars. If you're identifying a person not accurately on the pixel or the subpixel, I'm sure it doesn't really matter. But maybe someone can correct me. But coming to our industry, it's not good enough. So running algorithms that we are developing, segmentation algorithms on our benchmark, which is related to the semiconductor industry, the requirement is mean OU of 90–95%. Less than that is not good enough. We'll get to the wrong conclusions. So I'll summarize what we talked about. We talked that for AI, we need data, we need a place to store this data, and we need computing power. And for that, we need to improve our devices. We need to improve our memory devices, and we need to improve our processors, or GPUs, or whatever. But for that, we need AI. So that's a circle that will probably exist all the time. We are doing algorithms to improve the devices that will serve algorithms. So I will conclude with that. Don't ask what the AI can do for you. Ask what the AI can do for the AI. Thank you.